Hello everyone and welcome to another lecture, another online lecture for Math 837. The topic for today is alternating series. As always, let's start with a very brief recap of what series are. So we defined a series as simply an infinite sum of a sequence. And this is how we denoted it. K equals 1, infinity of AK, where AK is some sequence of real numbers. And we defined convergence of series as the limit of the partial sums. So we said that a series, an infinite series, k infinity, is equal to a value L if the limit of the partial sums as n goes to infinity, Sn is equal to L. And to determine the convergence or divergence of a series, aside from using the definition, we've covered a few tests. We've covered the divergence test, we've covered the integral test, and depending on when you're watching this video, we've talked about the comparison test. Today we're going to talk about, the comparison test and the integral test only work for positive series, so today we're going to talk about a new type of series which are called alternating series. So let me start with a definition. So definition. An alternating series is a series of the form equals 1 to infinity of -1 to the power of k times ak, or k equals -1 to the power of k plus 1 a to the k, where ak is a sequence of positive numbers. So here the -1 to the power of k or -1 to the power of k plus 1, depending on if k is odd or even, will be either -1 or +1, which means that if we write this series out, we'll have a positive term, a negative term, a positive term, a negative term. And we choose k or k plus 1, these two form, depending on whether the first term is positive or whether the first term is negative. Right, so if I expand the series out, k equals 1 to infinity of -1 to the power of k ak, I get, well, for k equals 1, -1 to the power of k is negative, so it's minus a1. And then for k equals 2, it's positive 1, so it's plus a2, minus a3, plus a4, minus a5, and so on. And if it was k plus 1, we would have, if it was -1 to the power of k plus 1, we would have a1 minus a2 plus a3 minus a4 plus a5, and so on. And this goes off to infinity. Now note that it's really important here that ak is a sequence of positive numbers, because if for example a1 is not positive, if a1 is negative, the first term is still positive, so it defeats the purpose. So the condition that ak be a positive sequence is quite important. Let me do a few examples, concrete examples, just to demonstrate some common alternating series. So let's consider the series -1 plus 1 minus 1 plus 1 minus 1, and so on. Now this series can be written in segmentation using in this form. So k equals 1 to infinity of -1 to the power of k. And we, so the first term, k equals 1, is just -1, the second term is +1, -1, +1, and so on. Now in this case, the sequence ak that we have in our definition is just equal to 1, because we can say this is equal to -1 to the k times 1. So the sequence ak is just equal to where AK is, or let me write it like this. AK equals 1. And of course this is a positive sequence. Positive sequence. Okay, another example we may have is something of the form 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. And this is the alternating harmonic series. We know the harmonic series is 1 plus 1/2 plus 1/3 plus 1/4. Here we're alternating the terms. So this can be written in sigma notation as, starting at k equals 1 to infinity, of minus 1 to the... So in this case, the first term is positive. So for k equals 1, we want a positive exponent, so this will be k plus 1. So when k equals 1, k plus 1 is equal to 2, so this the first term is positive. And then, and this is times 1 over k. So here AK is equal to the sequence 1 over k, which again is a positive sequence. Positive sequence. Now we can create an alternating series really by using any positive sequence AK. But what we really care about is, does it converge? So if we look at these examples, looking at the first one, the first partial sum, in this case S1 would equal to minus 1, and then S2 would equal to, S2 would be equal to minus 1 plus 1, which is equal to 0. S3 would be minus 1. S4 would be 0. So the sequence of partial sums goes minus 1, 0, minus 1, 0, which we know that that sequence diverges, in which case this series doesn't converge to anything. It's a divergent series. The second example it's interesting because we know that the harmonic series, when it's not alternating, is divergent. But in this case, because it's alternating, this series actually converges. Now, if this seems maybe counterintuitive because the harmonic series diverges, why would this series converge? Intuitively, the reason is the harmonic series adds up to infinity. As we keep adding numbers, it goes off, it blows up to infinity. But in this case, we're adding and subtracting. So that adding and subtracting effect cancels out, and at the end we get a finite value. So the first series we said was it diverges, and this one converges. But how do we show that it converges? So how to show? Now we could use a definition, but of course in this case, calculating the partial sums as a closed form would be very difficult. But it turns out that there's a very nice and easy test for alternating series to determine if they converge. And that leads us to the alternating series test. Alternating series test. And what the alternating series test says is, suppose we have a sequence of positive numbers, let AK be a positive sequence. With the properties that such that 1 is decreasing, so AK plus 1 is less than or equal to AK. Or sorry, it's strictly decreasing, so less than AK for all K. So strictly decreasing. And the limit as K goes to infinity of AK is equal to 0. So if we have a positive sequence that's strictly decreasing and it has a limit that goes to 0, then the corresponding alternating series converges. So then the alternating series that's given by minus 1 to the K k plus 1, k equals 0, sorry, to infinity of ak. Or in the case where we start the first term as positive, so it'll be minus 1 to the k plus 1 ak. K equals 1 to infinity. I should change the first one to k equals 1 as well for consistency. K equals 1. Both converge. So again, if we have a positive sequence that's used to define an alternating series, and that sequence has a property that it's strictly decreasing, and its limit goes to 0 as k goes to infinity, then the corresponding alternating series, whether we start the first term as negative or positive, they both converge. So let's first try to pictorially see why this theorem might be true. So we're going to consider the series starting with a positive term, so k plus 1 ak. We're going to consider this series. And let's consider the partial sums. So we have that S1 is equal to simply A1. And remember, AK is here as a positive sequence. So we're let's plot it out. Let's plot out. So this is the k-axis. And on this axis, we'll put SN, or SN, yes, right. And now let's put the first term, so S1 is here somewhere in the positive quadrant, so this is S1. Now S2 is equal to A1 minus A2. But A2 is positive, so that means S2 is smaller than A1. So let me write that down. So because A2 is greater than or equal to 0, S2 is less than, or A2 is actually strictly greater than, sorry, no, this is okay. So A2 is greater than or equal to 0, which implies that S2 is less than or equal to, S2 is less than or equal to S1. But also, we know that the sequence AK is decreasing, so we know that A2 is strictly less than A1, which implies that S2 is still greater than 0, right? Because it won't take us below 0. So let's draw S2 here on the plot. So this here is S2. And now similarly, S3 is equal to A1 minus A2 plus A3. Which we can also write as S2 plus A3. Now again, A3 is also greater than or equal to 0. So because A3, let me just separate these out. So because A3 is greater than or equal to 0, that implies that S3 is greater than or equal to S2. So we're going to go above S2. But also, because it's decreasing, AK that is, strictly decreasing, so because A3 is strictly less than A1, this implies that S3 is strictly less than S1, right? Because to get from S1 to S2, we subtract A2, and then we add a smaller value back. So we won't quite get back to S1, but we will be below S1. So if I plot this out, I'm somewhere below S1, but above S2. So let's say somewhere right here. So this here is S3. And then we repeat this process. Because the series is alternating, S4 will be below S3, but because the sequence AK is decreasing, when you subtract, you won't quite get back to S2. So S4 will be over here. And then S5 will again increase, but not go above S3, so it'll be S5 here, and S6 here somewhere, and so on and so forth. Now, because also we assume that the sequence AK is going to 0, the limit as AK goes to limit as k goes to infinity of ak is equal to 0. This means that these up and down jumps between the SNs will get smaller and smaller, which tells us that they will converge to some value L. Right, so if I keep plotting this out, I expect S7 to be here, closer to this line, S8 to be here. And again, remember, the jumps are getting smaller and smaller between, so S9 here, and so on and so forth. Now to prove this formally, the way we do is we consider just the odd or the even partial sums. And I'm not going to do a full proof here because the full proof has a lot of details which may take up too much time in the video. So instead, let me just do a sketch of the proof. So sketch of the proof. So again, we're going to consider the odd partial sums. So the odd partial sums. Right, so that's S1, S3, S5, S7, and so on. I.e. S2n plus 1 for n greater than or equal to 0. So if you write out the partial sum, S1 is equal to just A1, and then S3, remember we're only considering the odd ones, is equal to A1 minus A2 plus A3, which if I group the the last two terms, sorry, is equal to, A1 minus A2 minus A3. And then similarly, S5 is equal to A1 minus A2 minus A3 minus A4 minus A5. And then so on for S7, S9, S11. But note that since the sequence is decreasing, so since AK plus 1 is less than AK strictly, that implies that AK minus AK plus 1 is positive. So this is greater than 0. So since we're adding this factor in every consecutive odd partial sum, that implies that the sequence S1, S3, S5, S5, S7, so the odd partial sums is decreasing sequence. Remember, in this sequence, we're considering just the odd terms. So the S1 is actually the first term, S3 is the second term in the sequence, S5 is the third term in the sequence, S7 is the fourth term, and so on. And again, it's decreasing because every consecutive odd partial sum, we're subtracting a positive number. And if I go back to the picture, we can clearly see this in the picture as well. If we just consider the odd partial sums, which are above the line L, then we can see that they're in fact decreasing. Okay, next I want to show that this sequence is bounded. So I want to show that the sequence S1, S3, S5 is bounded. And the way I do this is, it's quite similar, but I write out S1 is equal to A1, and S2 is equal to A1, sorry, I'm only considering the odd ones, so it's S3 is equal to A1 minus A2 plus A3. And in this case, I'm going to put the bracket around the first two terms. And S5 is equal to A1 minus A2 plus A3 minus A4 plus A5. Right. So again, we know that it's an increasing sequence, AK that is. So AK plus 1 is decreasing. It's a decreasing sequence. So AK plus 1 is less than AK, which again, it's the same statement as before. AK minus AK plus 1 is positive, or in this case, strictly positive. Is greater than 0. So these odd partial sums are bounded below by 0 because we're adding a bunch of positive terms, right? The part in the brackets is positive, and the last term is positive because AK is a positive series. So therefore, S 2n plus 1 is a sum of positive terms, therefore bounded below by 0. So we have a decreasing and bounded below sequence. So S1, S3, S5, again the odd partial sums, is decreasing and bounded below, which implies by the BCMT that it converges. The limit as n goes to infinity of S2n plus 1 converges to something. Let's call it L. So going back to the picture, we've shown that the partial sums above the line L are converging to L. Okay, now we're going to consider, instead of the odd partial sums, we're going to consider the even ones. So consider S2, S4, S6, and so on. Right. In this case, we know that S2 is equal to S1 plus A2, S4 is equal to S3 plus A4, S6 is equal to S5 plus A6, and so on. So then the limit, or more generally, if I just write S2n, this is equal to S2n minus 1 plus A2n. So if I compute the limit for the even partial sums, so limit as n goes to infinity of S2n, this is equal to a limit as n goes to infinity of the even one, so S2n minus 1 plus the limit as n goes to infinity of A2n. And the first limit we just showed is equal to, it converges to some value L. And the second one, we know by assumption, is equal to 0, because we assumed that the sequence AK goes to 0 as n or k goes to infinity. So then the sequence of even partial sums also converges to L. And since S1, the sequence S1, S3, again the odd ones, S5, and the even ones converge to L. Both of these converge to L. This implies that the sequence, the combined sequence S1, S2, S3, S4, S5 also converges to L. And this is the part I'm going to omit to show this formally. This is done in the textbook, and you can do it using a bunch of epsilon n proofs, manipulations. But going back to the picture, basically what this shows is both the sequence of odd partial sums, which are above the line L, converge to L, and the ones below it both converge to L. So we can see just from this picture that the overall sequence of partial sums should converge to L, in which case the series should be a convergent series. So let's finish off with a few examples. So let's go back to the example we were originally talking about, which is the alternating harmonic series. So we had minus 1 to the k plus 1, 1 over x, 1 over k, sorry, 1 over k, from k equals 1 to infinity. So this is just the series 1 minus 1/2 plus 1/3 minus 1/4 plus so on. So of course this is an alternating series, where the corresponding positive sequence is ak equals 1 over k. And to use the alternating series test, we got to check that ak satisfies the conditions of the theorem. So the first condition was, is it decreasing? And well, in this case, or sorry, strictly decreasing. So in this case, because k plus 1 is strictly greater than k, that implies that 1 over k plus 1, which is equal to ak plus 1, is strictly less than 1 over k, which is equal to ak. So therefore, this is strictly decreasing. Okay, and moreover, the limit, and the limit as k goes to infinity of ak is equal to, well, it's just a limit as k goes to infinity of 1 over k, which is equal to 0. So these are the two conditions for the alternating series test, which implies that the series we started with is convergent. So therefore, the alternating series minus 1 to the k plus 1 over 1 over k is converges. Okay, let's do one more example. So let's consider the series starting at k equals 1 to infinity of cosine pi k over the square root of k. Now, right off the bat, this does not look like an alternating series, but note that cosine pi k is equal to 1 if k is k even, and otherwise it's equal to minus 1 if k odd. So we can actually simplify the series to be equal to series k equals 1 through to infinity of minus 1 to the power of k plus 1 over the square root of k. And this is the alternating series, with the corresponding positive sequence being alternating series, where ak is equal to 1 over root k. So since it's an alternating series, we can apply the alternating series test. So we got to check the conditions for that. The first one is the sequence ak equals 1 over square root of k strictly decreasing? So this is because k plus 1 is greater than k, strictly greater, which implies that the square root of k plus 1 is strictly greater than k, which implies that 1 over square root of k plus 1, which is equal to ak plus 1 is equal to, or is less than, strictly less than, 1 over square root of k, which is equal to ak for all k. So therefore this is strictly decreasing. And of course the limit as k goes to infinity of ak, which in this case is the limit of 1 over square root of k. Well, this one's equal to 0 because, again, the denominator is getting larger, so it goes to 0. So therefore, by the alternating series test, the sequence, which again doesn't look like an alternating series, but it is, cosine pi k over square root of k converges. So that's the alternating series test. Anytime you see an alternating series test, the first thing you go to tool should always be the alternating series test. I'm going to stop there. Thank you for watching. And a reminder again that if you have any questions about this lecture or anything else, I'm always available on Piazza. I follow it regularly, so if you have questions, it's posted there and I'll get back to you.